Hello and welcome to yet another video of Cornerstones of Math. In this video, I am going to count the number of functions satisfying different conditions. Moreover, I will relate those number of functions with basic combinatorics knowledge, such as permutation, combination, etc. Here, set X, which is domain, has m distinct elements, and set Y, which is codomain, has n distinct elements. All elements are real numbers. Find the number of functions f from x to y for each cases. For the first problem, we just have to find the number of all possible functions without any restriction. In the next problem, f is injective, also known as one-to-one function. In the next problem, f must be bijective, or also called one-to-one correspondence, or one-to-one and onto function. For the next problem, we have the condition that if xj is greater than xi, then fxj is greater than fxi, which implies the increasing function. The problem next is similar, but now we have if xj is greater than xi, then fxj is greater than or equal to fxi, which means monotonically increasing function. Finally, we will consider the case where f is surjective, or onto function, which means the function where the range fx equals codomain y. This final case is not easily generalizable, so we will find the exact number of functions only for the special case where m equals 6 and n equals 3. Alright, first, the number of functions in general when there are no restrictions. Here we have to pick the values for fx1, fx2, fx3, so on, fxm from the codomain y1, y2, y3, yn, having n elements. So for fx1, there are n choices, and for fx2, there are also n choices, and for fx3, there are also n choices, and so on, and for fxm, there are n choices. So we have n multiplied m times, which gives n to the power of m. This is the permutation with repetition. That is, the number of ways to choose m elements from the set of n elements and arrange them in a straight line, and we can choose the same elements multiple times. So that was the first problem. Next, f is injective, or one-to-one, or satisfying this fancy expression. Here we start the same. For fx1, there are n choices. However, if f is injective, then once an element is chosen for the value of fx1, that element cannot be the value of fx2. Therefore, for fx2, there are n-1 choices remaining. And of course, for fx3, there are n-2 choices, and so on. And for fxm, we have n-m plus 1 choices, which is really not that difficult to think of. So we have n times n-1 times n-2 times n-m plus 1. This is what we normally call permutation, when the repetition is not allowed. It is often denoted as npm, and it can be also calculated by n factorial divided by n-m factorial. So that was the number of injective functions, and now let's move on to bijective functions. Bijection, or one-to-one correspondence, is possible only if m equals n. That is, x and y have the same number of elements. Therefore, from our previous injective case, the number of choices decreases all the way down to 1. So we have n factorial, or m factorial, since m equals n. Now the functions with the property, if xj is greater than xi, then fxj is greater than fxi, which means increasing function. Here we need to establish some increasing ordering. So without loss of generality, let's say that the elements of x are x1, x2, x3, xm in an increasing order. so that x1 is the least element and xm is the greatest element. Now the codomain. Let us choose m elements from codomain y, and let's arrange them in an increasing order. Then we can write these m elements as y1 prime, y2 prime, y3 prime, and so on, all the way up to ym prime, using prime notations when arranged in an increasing order. Then if we let y1 prime as fx1, y2 prime as fx2, y3 prime as fx3, and so on, and ym prime as fxm, then we automatically have this inequality relation. Therefore, the number of functions is n choose m. The combination without repetition, which is also written as ncm, and also can be calculated by n factorial divided by m factorial times n minus m factorial. Now what about monotonically increasing functions? Well, the process is the same as for strictly increasing functions. Let's assume without loss of generality that elements of x have this increasing order. And let's choose m elements from the codomain. But now we choose m elements allowing the repetition. We can choose the same element multiple times. Then these m elements can be written in a manner that y1 prime is less than or equal to y2 prime, which is less than or equal to y3 prime, and so on, and less than or equal to ym prime. Remember, now these variables can have same values. Then letting y1 prime as fx1, y2 prime as fx2, y3 prime as fx3, and so on, we have this ordering, and we are done. This is the combination with repetition, denoted by using double parentheses, or also as nhm, often read n multichoose m. We can compute its value using the property that n multichoose m is equal to n plus m minus 1 choose m. For the derivation of this property, someone actually made a really good video on that. And finally, perhaps the most complicated one, the number of surjective functions, or onto functions, or the functions where the range equals codomain. I am not gonna waste your time, so I will explain how to do it right away. There are more than one method to solve this problem, but in here I will use partition of sets. We have to divide the domain X into n groups or subsets, where each subset contains at least one element. This number of ways to partition the set is often denoted as Sm, n, or m choose n notation with curly brackets, and often called the Stirling number of the second kind. But instead of that unintuitive name, let's remember it as the number of ways to partition the set having m elements into n non-empty subsets. Once we've finished partitioning, we have n distinguishable subsets. Next, we have to determine which subset corresponds to which element of the codomain Y. In other words, we have to distribute these n subsets to n distinct elements of Y. And there are total n factorial ways to do that. Therefore, the number of surjective functions is given as Sm, n times n factorial. This Sm, n does not have a simple general expression, so let us think about special case where m equals 6 and n equals 3. Number of surjective functions when x has 6 elements and y have 3 elements. Obviously, by our formula, it is S6, 3 times 3 factorial. But how do we calculate this S6, 3? First, we have to think about this. When we partition the set with 6 elements into 3 non-empty subsets, what would be the number of elements in each subset? In order to answer that, we must first try to partition the number 6 into the sum of 3 natural numbers. And you can easily find that 6 can be expressed as 4 plus 1 plus 1, or 3 plus 2 plus 1, and 2 plus 2 plus 2. Now let's compute the possible number of partitions for each cases. And let's actually try this case first. That is, partitioning into 3 subsets having 3, 2, and 1 elements respectively. First, out of 6 elements from domain, we choose 3 elements for the subset having 3 elements. So we have 6 choose 3. Then we have 3 elements left, and we choose 2 elements for the next subset, so we have 3 choose 2. Then we have only 1 element, and we choose 1 element for the last subset. So we have 6 choose 3 times 3 choose 2 times 1 choose 1, which is 20 times 3 times 1, which is 60. Next, partitioning into 3 subsets having 4, 1, and 1 elements respectively. Let's do it in the same way as in the previous case. So first we have 6 elements and we choose 4. Then we have 2 remaining elements and we choose 1. Then we have 1 remaining element and we choose 1. And we are not done here, because now we have to think about duplication. You see, because now we have 2 subsets having same number of elements, which is 1, we have just counted the same partition twice. For example, suppose that we have chosen x1, x2, x3, and x4, then x5, and then x6. And let's consider another partition where we chose x1, x2, x3, x4, then x6, and then x5. These two are the same partition, but it is counted twice. Therefore, we have to divide the entire result with 2, or more precisely, 2 factorial. This gives 15 times 2 times 1 times 1/2, which is 15. In the final case, partitioning into subsets having 2, 2, and 2 elements. So from 6 elements we choose 2, then from 4 elements we choose 2, and then from 2 elements we choose 2. And we have to think about duplication. Here, 3 subsets have the same number of elements, so the same partition is now counted 3 factorial times. This is the example of duplication when the subsets are x1, x2, x3, x4, and x5, x6. And these 6 are all same partition. Therefore, we have to divide it by 3 factorial. So we have 15 times 6 times 1 times 1/6, which is 15. Therefore, the total number of partitions S6, 3 is 60 plus 15 plus 15, which is 90. So this is the number of ways to partition the set. And we have to distribute each subset to the elements of Y. There are 3 factorial ways to distribute these 3 subsets to y1, y2, and y3, so the number of surjective functions is 90 times 3 factorial, which is 540. To summarize, the number of functions is given as n to the power of m, which is permutation with repetition, and the number of injective function is given as permutation npm, which is without repetition, and the number of bijective functions, or one-to-one correspondence, is given as factorial, and the number of strictly increasing functions is given as combination and choose m without repetition, and the number of monotonically increasing function is given as combination with repetition and multi-choose m, and finally the number of surjective function or onto function is given as Sm, n times n factorial, where this Sm, n means the number of ways to partition the set having m elements into n non-empty subsets. And that was all for today's video. Thank you for watching, and please don't forget to hit the like and subscribe buttons if you enjoyed this video, and I will see you in another video.